housekeeping items before I turn it over to today's speakers. Today's webinar is being recorded, so we're recording along with slides will be posted to our website in about 10 days. I will also send out an email once those do post to our website. So just keep your eyes and ears open for that. Everyone is on mute today, but we encourage that if you have questions during the webinar to submit those via the question box on GoToMeeting, and we will address those during a quick Q&A at the end of the webinar. And any questions that we can't get to today, we will be able to follow up with you via email after the webinar. So definitely, I encourage you to submit those questions. And then just to make everyone aware, this is a series and we do this every month, so I encourage you to just check back to our website for future webinars. It's also listed in our newsletter every month. So I encourage you to look back, and hopefully maybe there'll be other topics that you find interesting. So we will be having a webinar in April, and details on that will be posted to the website here in a couple weeks. On that note, I'm going to turn it over to Demetrius Papageorgiopoulos. He's the Fuel Cells Team Lead for the U.S. Department of Energy Fuel Cell Technology Office. Demetrius?
Thank you, Ali. Welcome, everyone. It is a pleasure to introduce the three presenters of today's webinar who are going to highlight the use of the rotating disk electrode technique to measure oxygen reduction reaction activity in fuel cell applications. Dr. Shyam Kocha carried out his PhD at the University of Hawaii and postdoctoral research at the National Renewable Energy Laboratory in the area of photoelectrochemistry and water splitting. Subsequently, he embarked on fundamental and applied R&D in the fuel cell industry, including UTC Fuel Cells, General Motors Corporation, and Nissan for about a dozen years. His research focus spanned platforms from half cells to large-scale PMFC stacks for automotive applications for the improvement of performance, durability, and cost. His current position is that of Senior Scientist at the Hydrogen Technologies and Systems Center at NREL. Dr. Yannick Garçonnet is a Senior Scientist for Exit Incorporated in the Alternative Energy Section in the Chemistry Division at the Naval Research Laboratory on PEM fuel cell related activities, including electrocatalysis, poisoning, and recovery of catalyst layer and other renewable energy electrochemistry. Yannick has a PhD from the University of Southampton in the United Kingdom in the area of electrochemistry and corrosion. Dr. Debbie Myers, who is our third presenter, is the leader of the Hydrogen and Fuel Cell Materials Group in the Chemical Sciences and Engineering Division at Argonne National Laboratory, where she has worked on numerous fuel cell-related activities, including most recently on durability of platinum-based polymer electrolyte fuel cell cathode electrocatalysts. Debbie holds a PhD in chemistry from the University of Urbana-Champaign. And with that, I will hand it over to Shyam.
Thank you, Demetrius, and thank you all for joining the webinar today. The outline of the talk is as follows. I have a couple of slides on the background. Then I'll talk about the experimental aspects of RD testing, the basic measurement technique, although a lot of you may already have conducted RD experiments, so it'll be brief. The parameters affecting RD activity measurements, that'll be the main part of the talk. And finally, durability measurements using RD. After the summary, Demetrius will talk about the next steps. So in this background slide, what I wanted to say was the RD technique is becoming very popular for evaluating small quantities, tens of milligrams of catalysts that are synthesized in laboratories all over the U.S. and the world. The RD technique is especially suited to evaluating small quantities of catalysts, so you don't have to scale up every single catalyst. Unlike an MEA, where you would need hundreds of milligrams of catalysts to test in a subscale fuel cell. The other thing is that the trend of activity and durability in RD measurements can be used to predict the trends of activity and durability in PMFCs. I stress and emphasize on the word trends because the absolute values of activity in RDE and PMFC are not expected to be the same. And I've expanded on that subject. As you can see next to the graphic of the MEA, where you see a 10 micron catalyst layer next to a membrane, and on the extreme right you see a RDE 5 millimeter disc. In an RDE, what you have really is dissolved oxygen in the electrolyte, not a gas flow through flow fields like in a PEM fuel cell. Also, the interface is a platinum on carbon, most often with a certain amount of Nafion incorporated into the catalyst layer or as a cap to the RD electrode, and then acid. The pores in the catalyst layer are flooded in RDE, as opposed to having gas and water pores in an MEA of a fuel cell. The electrodes in RD are very thin, 0.1 micron or so, instead of 10 microns for an MEA. The electrolyte in RDE that we use these days to mimic fuel cells is perchloric acid, and the acid provides all the protons necessary for protonic conduction, whereas in a PEMFC you actually need ionomer in the catalyst layer, and that provides protonic conduction. In RDE, you don't really need the ionomer for protonic conduction, but mainly as a binder and dispersant in the ink. The other thing is the measurement technique. RDE, we usually use a scan rate of tens of millivolts per second, whereas in a fuel cell it's more realistic at about 15 minutes per point. The loadings in PEMFCs are about 0.4 milligrams per centimeter square, whereas they're about 4 to 36 micrograms per centimeter square. So as you can see, the systems are quite different, and they will provide, the RD does provide the same trends for in most cases for catalyst activity, but the absolute values should not be expected to be the same. Before going on to the experimental aspects, I just wanted to list a whole bunch of other things that you can get from RD measurements. Using a cyclic voltammogram, which is carried out on a nitrogen, you can measure the surface area of the ECA using HUPD, CO-chem absorption, and copper UPD. You can also get AA capacitance, pseudocapacitance, which really means some of the oxide coverage on platinum or whatever the platinum-based catalyst is. You can also look at corrosion of supports and look at the onset potential of support corrosion. You can, of course, get durability studies, but only for limited short times. Using the IV curves under oxygen, you can get the activity of all kinds of catalysts. And lastly, I mentioned non-PGM catalysts, which we won't be touching upon in this presentation. We're mainly talking about platinum-based catalysts. You can also get fundamental kinetic parameters like reaction order with respect to oxygen partial pressure, Toffel slopes, effect of contaminants in electrolyte reactant gases, anion absorption, and so on. If you use an RRD, a rotating ring disc electrode, you can also get peroxide generation. There are a whole bunch of complementary techniques like EIS, impedance, EQC, and all that can also be used along with RD to get more information. So now we move on to the experimental aspects of RD testing. On the top left over here, you see a typical setup, an RD setup, where you see a rotator, an autolab potentiostat, samples, gas flows for the reaction, and so on. What I really wanted to point out in this slide is that, which I've marked in red in the bottom right, is that the contamination of cell and electrolyte poisons the platinum catalyst and is one of the primary reasons for low and scattered activity data. So as a result, we have to do a lot of cleaning of the glassware to make sure that it is pure and clean. One of the cleaning techniques is to use acid, concentrated sulfuric acid, and followed by an oxidant, either nitric acid or concentrated sulfuric acid mixed with no chromix. This kind of cleaning is carried out maybe once or twice a month, depending on how much you contaminate your cell. But the one that's done more often is boiling in deionized water. One needs to wash or boil the cell in deionized water and change the water about 6 to 8 times in order to clean the cell properly. And how do we figure out if your cell is clean or not? One of the ways is as follows. Using a polycrystalline platinum disc, which is reusable, if you obtain a specific activity of greater than 2 milliamps per centimeter square, as shown by the red bar over here, you can say that the cell is fairly clean and good enough at least to evaluate high surface area catalysts like platinum on carbon, shown in the small bars on the right. If the platinum polycrystalline activity is less than 1.5 or 1 milliamp per centimeter square, you're likely going to be have some contamination at lower values. This next slide, I just wanted to show you the equipment that we use for ink formulation electrode preparation. You need a sonicator, such as a horn sonicator or a bath sonicator. a nanobalance to measure the quantity of catalyst that you're applying to the RDE, and ink deposition. The ink deposition portion is a bit of an art. You need steady hands for sure, and as you can see, you've got to drop about 10 microliters of the catalyst ink onto the RDE tip and then dry. Before making any measurements, the first thing we do is conditioning or break-in. Unlike PEM fuel cells, the conditioning is much shorter and simpler. You just need to cycle it for about 50 or more cycles over a certain voltage range depending on the catalyst. And you notice the CVs, they kind of evolve until the CV becomes invariant with time, and then you know that your catalyst has been conditioned. So here's an example of the measurements you get from RDE. On the top left, you see ORR curves. These are IV curves under oxygen, taken at various rotation speeds from 400 RPM to 2500 RPM. On the bottom, you see a typical Kurecki-Levick plot at different potentials. If you look at the pink curve or line at 0.9 volts, you see the data for all the different speeds, and that can be extrapolated to 0, where 0 is the x-axis is 1 over square root of the speed. So that corresponds to something theoretically an infinite rotation speed, giving you a number that is as close as possible to being mass transport free. On the right side, you see a peroxide curve, and below that you see an IV curve. Very often people take the IV curve only at 1600 RPM or just one speed, because you don't need, it takes a lot of time to do all the speeds. And if you do it just at 1600 RPM, the limiting current is expected to be about 5.7 milliamps per centimeter squared. You can get peroxide currents, and that's very useful in order to understand the reaction taking place. Here's an example of an RD test protocol. On the top right, you see a triangle, which shows you a voltage profile of the protocol, going from 1 volt to 0 volts. What I wanted to point out on the IV curve is that you have two different scan directions. You can go anodically or cathodically, and as you can see, you'll get a different number for the activity at 0.9 volts, depending on which direction you go. So, so the protocol parameters, such as scan direction, scan rate, and voltage range, are all going to affect the measured activity. And the main reason for this is the coverage of the platinum with oxides. The coverage is going to be different depending on how you choose your parameters. So the protocol is definitely going to affect what you measure. At this point in time, there are no standard protocols, so people in the literature use all kinds of different conditions, and it's very hard to normalize those. On the bottom right, you just see an example of the ECA, the specific activity and mass activity extracted from the data at 0.9 volts from the IV curves. One other thing about the protocol and the measurement, I wanted to talk about the corrections applied to our IV curves. I won't go into the details of this, but one needs to do a background current correction. And what we mean by this is simply the CV measured under nitrogen has to be subtracted from the IV measured under oxygen, just to take care of the background. Secondly, we need to correct for the solution resistance. For 0.1 mole of perchloric acid, the resistance is about 20 ohms. Some potentiostats like the auto lab make this correction in situ, but all potentiostats do not do that. Lastly, corrections for oxygen partial pressure. If you're in a lab like Enroll or Los Alamos at an elevation, you have lower ambient pressure as low as 83 kilopascals or even lower. And so corrections must be applied so that you can normalize the data to 100 kilopascals so everyone can compare. At this time, we're going to switch into the parameters affecting RD measurements. And before I pass it on to Yannick, we have broken up the parameters into ink formulation, electrode, and deposition of film. At this time, Yannick will focus on film quality and uniformity and rotating and stationary methods of drying and forming films. Yannick?
Yes, so thank you, Sham. So, so typically what we do is we cast the film, as Sham was saying before, and you know, and we let the film dry, what I call stationary drying. And over, you know, when you look at what the film looks like, you can have different kinds of films, and that's what the pictures on the left side is showing. So I've called these like 3 different categories. What I call a bad film, and typically what I see is some kind of a coffee rings on the outside, and so very uniform on the outside, not that uniform in the center. And then you have what you can call intermediate films. If you look at it, it looks much thinner in the center and a little bit more uniform. And then when you have the good film, you don't really see any of these differences. It looks pretty uniform. And then if you look at the electrochemistry on the other side, so you look at the CV, and on the top, you can see that when you have a bad film, your surface area that you're going to measure for hydrogen is going to be much smaller compared to the intermediate films and the good film. And so typically the category of films that one might get is the intermediate and good films. And when you look at the OR curve, you can clearly see that depending on how your film looks like, your OR curve is going to be very different. You might not reach the limiting current perfectly, and the values of current you're going to measure at 0.9 volt is going to be very different depending on how the film looks like. So on the next slide, next slide, please. Can I get the next slide, please?
Yeah.
Sorry, we're delayed here today. It's just moving slow.
So
go ahead.
If we do a study and look at how a stationary film would look like, so we in this case I looked at on the microscope, optical microscope, again, so we see fairly uniform on the edge, and it's a very thin film in the center of the electrode, and we have a coffee structure at the so a coffee ring structure at the edge. And if you do SEM pictures, again you see the same thing. You see very thin film in the inside of the electrode, and more dense and homogeneous film on the outside of the electrode. And when I try to do a 3D optical profilometer on the film, you can clearly see that you don't have a uniform film, and it's a very coffee ring structure. And this is predicted in the literature. I mean, the papers by Jonker and that in Nature clearly shows how films dry. They even have a movie showing how films are going to dry when you do it stationary. So how do you move away from that? So the way I did this is by trying to change the way we dry film, and then doing a rotational drying method while I dry the film. So on the next slide, we're going to compare the difference between having a rotational film. So when you do a rotational film, under the microscope, typically the film looks very uniform over the entire glassy carbon surface, and we don't really see a coffee ring structure. And if you do SEM of that same film, again, it's a very dense film over the entire surface, and a 3D picture shows that we have a very uniform film. We might have a little bit of a ridge on the outside. So now if we look at the electrochemistry, how the rotational versus the stationary films, so that's what's going to be shown on the next slide. So you can see here we have 2 different catalysts. So on the top it's E-Tech, and on the other side is Johnson Matthey. So when you look at the CV, the CV is not that much affected by how the film looks like. But when you look at the again on the oxygen reduction curve, you can clearly see that the rotational film, the current that you're measuring at 0.9 volt are much higher, and you reach a much nicer limiting current plateau than you do on a stationary film. And that's true for both catalysts that when we look at it here. And so if you look at the reproducibility of the method, and that's going to be shown on the next slide, where we did the test for so 7 film stationary versus 7 film rotational in succession. You can clearly see that both in terms of platinum surface area, mass activity, and specific activity, that the number that you get with a much more uniform film is always going to be better than what you get if you have a stationary film. So it's very important to pay attention to how the film looks like, and making sure you always have a nice uniform film. The other thing that is important to look at is the ink formulation, and this is what we're going to focus on right now. So we're looking at how that affects performance. So a lot of time and effort is spent on optimizing the ink formulation for the catalyst layer and the MEAs, but is it is it necessary to do the same thing for rotating disk electrode testing of catalysts? So if you do, this is based on a paper published by Sham a couple of years ago, showing how the ink formulation affects the platinum surface area of the catalyst. And this is done for, on the top here you have two different catalysts. It's a TKK catalyst, heat treated and non-heat treated. And you can clearly see, especially on the blue curve, that there is an ink formulation, an optimum ink formulation where you're going to have to get the highest platinum surface area. So it is important to, for one to spend a little bit of time optimizing its ink formulation while, when it's testing its catalyst, because you might not get necessarily the true platinum surface area, and it's important to spend time looking at that. And again, on the next slide, what we did is looking at, for a TKK catalyst, the same TKK catalyst that was, on the previous slide, for, in different papers, over the last few years, how the platinum surface area, measured for this catalyst is not, the same. Again, the conditions are different, but clearly in all these papers, the ink formulation is also, very different. So when you have the optimized ink, the surface area is close to 105, and then when you change the water, if you just use water, if you use Nafion, or you put IPA versus ethanol, you get different, different measurement. And this is just a small sample of what's outside in the literature. There are, we could not fit all of them on the graph, but, there is papers where you have much lower surface area. So it's important to, spend some time optimizing the ink formulation. Next slide. So now, if you try to look at a baseline platinum activity, it is possible, to get, the same numbers in terms of, mass and specific activity for different labs. These are not optimized films, and not all the parameters are optimized, but at least we can see that in terms of activities, this is from GM, Nissan, and NRL and NRL. When the film looks about the same, if they do look the same, we do get about the same activity. And none of these films, have Nafion. All of these films have Nafion incorporated. Sorry, but we do get some numbers in terms of activity. Next slide, please. Now, again, if we start looking at optimization, when we do optimize the films, and in this case, we're looking at, NRL, we tested 20% platinum of alkaline carbon E-Tech, and NRL for this, the TKK catalyst. So when you have a stationary film, you can see the activities, and then when you, do a rotational films, you can see that we have an increase in activity by about 1.5. Now, if we start looking at taking IR, corrected curve, you can see again that the activity is going to, increase, by another 1.5. And in the case of NREL, where they looked at, the influence of Nafion, again, when you start doing all these optimization process, you start to see, better and better number. So, there is probably a role here for us to look at in terms of optimizing ink formulation and films and all that when we do RDE testing. Next slide, please. So now I'm going to pass it back to Sham, and he's going to talk about the effect of Nafion in the ink formulation.
Thank you, Yannick. So in delving more into all these parameters that affect the activity, what we wanted to do in our study at NREL was that we wanted to see if we can make these inks and films without using any Nafion. Can Nafion be eliminated? Because Nafion ionomer in the film can help you disperse the catalyst. It also acts as a binder for the catalyst film. That's the reason why most people use Nafion. But in excessive quantities, it can affect the oxygen transport resistance if it's too thick or non-homogeneous. It can also affect the electronic resistance if it's too thick. And to a very small extent, it might even cause anion absorption due to the sulfonate anions. So we wanted to try to formulate inks that did not have any Nafion in them. So this is data, about 45 or 50 data points taken over a period of 6 months on and off, not continuously, in which we tried a whole bunch of things. All these inks did not have any Nafion. Initially, we started with the platinum on carbon, with just water, the simplest ink possible. But the dispersion was not very good. It flocked and precipitated very easily. We then added a little bit, reintroduced some IPA into it. It got a little better, but not good enough. Finally, we changed from bath sonication to horn sonication and changed sonication times. None of these things really helped in the sense that, as you can look at the data, you have a mean of about 387 micrograms per centimeter square for the specific activity, but the standard deviation is very large. The data is basically scattered, and from day to day you would get different results. And so this data is completely unacceptable. On the other hand, the fact that for Nafion catalysts, as I'll show later in the next slide, the mean value for the specific activity is closer to 275 micrograms per centimeter square, and this one is 387. Not only that, you have quite a few data points at these high specific activities over here. So this kept us going because we wanted to get reproducible high numbers for activity, if at all it was possible. So this slide shows you the final results summarizing what we did. You have 3 sets of data. I've eliminated the data points just to reduce the clutter. So you just have 3 Gaussian distributions based on, 30 to 50 data points each. We have data for Nafion-based inks. That is a red curve over here showing you about 275 micrograms per centimeter square. It's a very narrow distribution. The black curve is the same as what you saw in the previous plot with a broad distribution, but it's not very good. Finally, we succeeded in getting a fairly high activity of 500 micrograms per centimeter square with a narrow distribution, as you see in the blue curve. So how did we do this? It already says so in the title. We added some surfactant. What happened is I went to the lab next door, and a long time ago we had used some surfactant for PEC studies. And so I introduced a bit of surfactant in order to disperse the ink better. The result was that we formed very good dispersions and very good films. But once you put it in acid, they washed off, produced a lot of pretty bubbles too. So that did not work initially. We kept reducing the amount of surfactant until we used just about 2 microliters of surfactant. That gave us a reasonable dispersion and also a reasonably good-looking film. It still wasn't a perfect film, but the data was now much better, less scattered, and a much narrower distribution of values. So to summarize those results of Nafion studies, we looked at 2 catalysts, platinum on high surface area carbon or Ketchen black, and platinum on Vulcan. In each case, we found a 1.8 times increase when we eliminated Nafion from the ink. One of the things to note is that the ECA, the blue bars that you see, stay constant. So we had 100 meters square per gram, no matter whether we had Nafion or not. So there's no problem for protons or electrons. The improvement was in the specific activity of the red bars, which led to an increase in the mass activity. Now, the reasons for an improvement in the specific activity can be only faster reaction turnover times or better oxygen transport and more oxygen. So we wanted to go a little bit deeper into this and understand what's going on and why we get these such high values without Nafion. Here's some schematics that helps us come up with a hypothesis for what's going on at the interface. On the left, you see platinum on carbon with a fairly uniform, thick Nafion film, and then perchloric acid. So the interface that's typically studied in RDE is the left one. And what you have is the Nafion or ionomer film that's soaked in perchloric acid. It's a pretty complex system. Very often, if you put less Nafion, you'll have a patchy film. And in some areas, you may have large amounts of Nafion that may cause electronic resistances. Finally, in our case, we eliminated the Nafion, and so we have a simple, clean interface with perchloric acid with a catalyst. So we looked at SEM micrographs of these catalyst layers for 4 cases: no Nafion, standard ink of 40 microliters, higher Nafion content, and finally super high 2.4 ml of Nafion. Those are the SEM images on the top. The left column is for no Nafion. As you can see, we didn't have Nafion, so the fluorine signal is just a background, what you see. The platinum is still in the form of a ring. I mean, you do have a catalyst in the center, but there is a clear ring that is formed. In the case of the standard ink, you have platinum forming a ring at the edges, a coffee ring, as Yannick explained, but you also have fluorine or Nafion in the same area. So you see you have this ring at the edge of platinum on carbon with Nafion, and obviously that can cause oxygen transport issues. I'll just go to the last case of the 2.4 ml Nafion. You can see the fluorine signal is very strong. It has a large amount of Nafion in it, and you can barely see the platinum and carbon signals. If you look at the IV curves for oxygen very carefully, for the case of no Nafion, 0 microliters, or with Nafion, standard amounts, you see the red curve is very sharp, and the limiting current is closer to true limiting currents. It's not so rounded. You can take this data and plot it in a Toffel slope, in a Toffel plot. It's a semi-log plot, and you see that the Toffel slopes are lower. You can use a single Toffel or a double or triple Toffel. It's not important, but the main thing is the Toffel slopes are lower, either due to faster reaction or more access to oxygen. Another study we wanted to do to investigate this oxygen transport or mass transport issue was to change the loading of the catalyst. The x-axis is the platinum loading, milligrams per centimeter square. Sorry, it should be micrograms per centimeter square. As you increase the catalyst loading, obviously the thickness of the catalyst layer increases. Now the blue curve corresponds to Nafion free. As the thickness of the loading increases, you see a loss in activity, so obviously there's some mass transport issues. In the case of Nafion, the curve is much flatter. Now I want to say that the data in the low loadings, we have more recent data that is better. When we took this data, the films were not of very high quality. As you can see, the limiting current started going down because the entire surface of the electrode was not covered with catalyst. But if you can make better electrodes with low loadings and thinner films, the red curve, for example, becomes linear and keeps increasing for quite a while. Lastly, one other effect of Nafion that we wanted to check was anion absorption. The plot on the top left is fairly obvious. It's been known for the last 20 or 30 years as to the anion absorption effect of the sulfate ion. If you look at the CVs for perchloric acid and sulfuric acid for platinum on carbon catalysts, you see that there's a shift in the onset of oxides when you use sulfuric acid. That is because there's anion absorption of sulfate anions in this area that shifts the oxide. The HUPD peaks are a little sharper for sulfuric acid too. This is well known. So what we did, and that's shown in the bottom right plot, is we looked at, sorry about that. We looked at perchloric acid, but for cases of catalyst layers that had Nafion or no Nafion. What we saw was hardly any shift in the onset of oxides. If any, the shift was in the wrong direction. So in our studies, we cannot say that based on these CVs that there is any anion absorption effect. But I must mention that in some work from Argonne National Lab from the Markovich group for polycrystalline platinum and 3M NSCF, they do see a small effect of anion absorption in those cases, but we don't. Okay. Now, there are some other aspects that I wanted to point out. One of them is the impact on particle size effects. If you look at the literature, there's a lot of data either supporting or not supporting particle size effect. More papers support it than do not. We took 2 pieces of literature by Meyerhofer and a GM paper, and those 2 data points follow roughly this blue curve and shows a fairly steep effect of particle size as you go from polycrystalline platinum to platinum black to smaller and smaller particles. Note that the y-axis is a log scale, so this is really steep, even steeper than what you see. In our case, we have data points. The red circles are for with Nafion, and the triangles are without Nafion for platinum on Vulcan and HSC. The ones without Nafion are much higher, as you saw before. And if you drew a straight line from polycrystalline platinum through these, it's somewhat more linear, again in a log scale. Mainly the point I want to make is that particle size effect seems to be much more shallow or less severe in the case when you don't have any Nafion. Okay. One of the last slides in the area of activity before we move to durability. In the first slide on the background, I talked about MEAs and RD and how you can predict catalyst activity in MEAs. using RDE in terms of trends, but not absolute values. Now here's some RD data from GM, Nissan, NRL, and NREL with Nafion in RDE. And you see that they're all very similar in this case. And they're also very similar to the MEA values, to activity measured in MEAs. Note that the MEAs were tested at 15 minutes per data point in very different conditions. So it's merely a happy coincidence that these values match the MEA values. We really shouldn't expect it. Because you can see with an Nafion free, or as Yannick showed with some better quality films, you get much higher activity with RDE than you get in an MEA. So the main point again was that the absolute values are not comparable, but the trends that you would see for different catalysts in RDEs are generally comparable to what you see in MEAs. And at this point, I'll pass it on to Debbie Myers of Argonne National Labs to talk about durability measurements.
Thank you, Shyam. So in this section of the talk, I'll talk about the factors affecting the durability measurements of catalysts and catalyst supports and the protocols that have been developed for platinum electrocatalysts specifically and those supports, both through the Department of Energy's Durability Working Group, and we have a website on the EERE related to the Durability Working Group if you want to know more about that, and also through the U.S. Drive Tech Team collaborations. So next slide. Previous slide. I think you did 2 slides. Thank you. So when I'm talking about durability, what I mean is the ability of a catalyst to maintain its electrochemically active surface area, which I've abbreviated as ECA, and its oxygen reduction activity with potential cycling protocols. And the various degradation mechanisms for platinum-based catalysts have been discussed extensively in the literature, and I just want to summarize them here, that the ECA loss and increases in particle size you see as a result of cycling can be associated with preferential dissolution of small particles, specifically less than 3.5 nanometers, redeposition of this dissolved platinum onto larger particles, which is driven by the higher surface energy of the small particles, and also redeposition between particles to cause coalescence. And I've shown a couple of micrographs from the University of Texas showing how this occurs, that you have deposition of platinum between the particles and you see long chains of particles, which results in a loss of electrochemically active surface area. And finally, you can also see corrosion of the support. And what this corrosion of specifically the carbon support does is causes loss of contact of the platinum nanoparticles with the support, loss of electronic contact, so those are no longer available for the electrochemical reactions. And also this corrosion of the support or erosion underneath the particles can cause the particles to coalesce, resulting in similar loss of ECA as what you see with platinum dissolution and redeposition. So the extent of the ECA loss that you see both in MEAs and RDE and also evolution of the particle size distribution depends on the extent of contributions from these various loss mechanisms. And that extent, or the contributions from the various mechanisms, depends on several factors, and the most important factor being the upper and lower potential limits of the cycling, the type of profile you use, whether it's a triangle or square wave, and the scan rate of that profile. It can also depend on, as I'll show in a couple of slides, the transport of dissolved platinum away from the electrode. So for example, if you're rotating or not rotating the electrode, if that platinum is transported quickly away from the electrode, then it's not available for redeposition for that ECA loss mechanism. It also depends on the ECA to solution volume ratio and on temperature that I'll show in a moment. Okay, next slide. So factors that can affect RDE durability measurements are the identity of the electrolyte, whether it's perchloric acid or sulfuric acid, specifically the pH of the electrolyte. So in some studies at Argonne where we cycled the electrode in 0.57 molar perchloric acid or half molar sulfuric and then compare the ECA loss, we see very similar losses for those two conditions. So here the 0.57 molar perchloric acid is chosen to match the pH of the 0.5 molar sulfuric acid. But if you're using 0.1 molar perchloric acid, you'll see losses that are less than what you see for the half molar sulfuric acid. So electrolyte identity is important in electrolyte concentration. Also, as I mentioned previously, the ECA loss depends on temperature. So as you increase the temperature, as I show in the lower right plot, you see increased loss of electrochemically active surface area and ORR specific activity. Another thing to keep in mind is that during the conditioning period that Sham mentioned, you can see considerable change in the particle size distribution as shown in the upper right plot. So just 32 cycles between hydrogen evolution and oxygen evolution can cause a significant change in the particle size distribution. So while you're actually measuring an increase in the ECA as you start to condition the electrode and remove contaminants from the surface of the platinum, you're actually changing the underlying surface area of the catalyst. Keep then if you're in conditioning protocol. Next slide, please. Next slide.
We are on the next slide.
Well, not for us.
Okay, so I'm on the slide that says ECA loss and dissolved platinum concentration.
Right.
Yeah, that's the next slide. You want me to go one more slide?
Well, on my screen, it's still showing factors affecting RDE durability measurements.
Hold on real quick.
There it is. Okay, thank you.
Oh, it's just really slow today. I'm sorry.
That's all right.
Okay.
So I want to mention that measurements in aqueous environment allows you to determine some things that can't be determined in the MEA environment. For example, you can determine dissolution rates of the metallic catalyst components, and this can be done, for example, by measuring the dissolved platinum concentration, or say if it's an alloy, like a platinum cobalt alloy, you can measure the cobalt concentration in the electrolyte using techniques such as ICP mass spec, which has a very sensitive detection limit for those two metals. And some example of this is a study by Toyota shown in the upper two plots where they measured the amount of dissolved platinum in the electrolyte as a function of rotation rate of the RDE, and seeing increased concentrations of platinum with increasing rotation rate because the platinum is transported away from the electrode surface, no longer available for redeposition. And due to this transport of platinum away from the electrode surface, in the upper right plot, what they saw was an increase in the loss of electrochemically active surface area with increasing rotation rate. So this points out the need for keeping the rotation rate the same as you're doing your durability measurements. So in the bottom right plot, what I show is that if you elevate the temperature of your RDE electrolyte and you also rotate the electrode at a fairly fast rate, you can see ECA losses that are very comparable to what's seen in the MEA environment. Next slide, please. So the durability working group of DOE has established several protocols for measuring both the catalyst durability and the support durability in an RDE environment. And many of these were then derived from what was established by the U.S. Drive Tech team for membrane electrode assembly environments. In the upper left plot, I show the catalyst protocol that was established by the durability working group. This is identical to the MEA protocol, so it's a triangle wave between 0.6 and 1.0 volts at 50 millivolts per second. It's recommended that you cycle it for 30,000 potential cycles, and in this case, the electrolyte temperature is room temperature. The Two plots on the right side of the slide show the support protocol. Now this is a protocol that's designed to minimize the loss of the platinum surface area due to dissolution and redeposition and focuses on the support. So as we're up at these higher potentials where you're forming an oxide on the platinum surface which passivates the platinum, you're specifically looking at degradation of the support. So the potential protocol in the upper right is for room temperature measurements, and this is a 1 to 1.6 volt triangle wave at 100 millivolts per second. And this protocol, which is 6,000 cycles, takes 24 hours to complete. So if you only have the room temperature capability with your RDE, we would recommend this protocol. However, if you can elevate the temperature of your RDE, we recommend the protocol on the bottom right, which is a 1 to 1.5 volt triangle wave at a faster scan rate. So the faster scan rate and the higher temperature accelerate the degradation. So in this case, we recommend 5,000 cycles rather than 6,000. And this protocol then only takes 8 hours to achieve the same degradation that you see at 24 hours for the upper right support protocol. So during these measurements, we recommend that you determine the electrochemically active surface area and OR specific and mass activities after a specific number of cycles, 10, 100, 1,000, 3,000, 10,000, 2,000, and 30,000 cycles. And based on what I showed here today, the parameters that we recommend reporting are the type of electrolyte and its concentration, the temperature used, the rotation rate used during the cycling, the method that you use for the measurement of the electrochemically active surface area, whether it's hydrogen adsorption or CO stripping, and also the constant used for calculating ECA, which is typically 210 microamps per square centimeter for the hydrogen adsorption region, but there's other, sometimes variation in that number that's reported. Mentioning also the scan rate and direction for the ORR measurement, which Shyam mentioned is very important in the final value for that ORR activity. The rotation rate during the measurement of the ORR and the reference electrode and the method used for converting that potential to the RHE scale. Okay, I'll turn it back over to Shyam.
Yeah, just a summary slide. I won't summarize the entire presentation, but I just wanted to point out that RD techniques are obviously useful for evaluating and screening the ECA and activity of and durability of very small quantities of catalysts for pendencies. A whole bunch of factors, including the protocol, affect the measured activity. And between labs, we don't exactly have a standardized protocol, so sometimes it's very difficult to compare results between labs or while you're reading the literature. So further work needs to be done combining the best practices. One of the things in RDE is that it's important also in a fundamental sense to try to approach the true activity. No one knows what the highest value of the true activity of the catalyst is, which is assuming the mass transport and resistance of 0, but that may not be the case as of yet. So in the interest of being able to compare results, it would be good to have a standard protocol. In slide 10, I had a rough suggestion of what such a protocol would be like. And acknowledgments from NREL, Argonne, and NRL. And I'll pass it on to Dimitrios, who will discuss a slide.
Thank you, Shyam. As discussed, it would be helpful if a standard test protocol is established for using the RDE technique. So as a next step, the DOE plans to solicit input from stakeholders in the research community, most likely via the release of a request for information later this year on a standard RDE test protocol. And as mentioned, this is most likely to be released later this year, not in the next week or so. But in any case, such a request for information is going to be communicated, posted on our site, which is listed on the slide. And for any questions you may have regarding this, specifically this, I have my email address on there, which is available. And with that, I would like to address, I would like the speakers to address some of the questions that listeners sent in. And the first one is related to the glassware cleaning procedure. And the listener is asking if there is a reference available for glassware cleaning.
So there are several papers, such as the ones from Yannick's group at NRL and from NREL. Different labs use different procedures, and the main thing to keep in mind is you need one strong acid like sulfuric acid perhaps that complexes impurities and washes them off, and a second one that's more oxidizing, either like Chromix, which is not used anymore because it's toxic, or a no Chromix mixed with sulfuric acid. But Yannick, do you want to comment on what you use for cleaning?
Well, that's exactly what we're doing, and like you were saying, I think the paper that we published in analytical chemistry, we do have some explanation in terms of how to, clean glassware and things like that.
Not exactly what you'd expect to wash your wine glasses with, I suppose. So I'll move on to the next question. It's kind of related to the procedure as well, and the listener wants to know what the best method to dry the thin film electrode after the ink has been deposited.
I'll start by saying what we do is we just dry it in an oven at 40 degrees centigrade or so. But I think you should look at Yannick's paper where he has used a rotational technique, and that definitely provides films that look much better. Yannick, any other comments?
That's correct, and what I've also been doing lately is using a fume hood that's laminated. You have a airflow on top of the electrode while it's drying. That seems to be helping, when you're drying the electrodes.
Okay. Debbie, is there anything? Sorry, Debbie, is there anything else you'd like to add?
Oh, I would agree with Yannick. That's what we do here at Argonne as well, have an airflow. What we do is put the RDE tip very close to a fume hood, and so just the suction of the fume hood provides a nice airflow over the tip.
Okay.
Okay, now this is a question to all speakers. Levich's RDE theory applies to infinitely thin electrodes. However, relatively thick catalyst layers have often been used lately to study, for example, non-precious metal oxygen reduction catalysts. Could you comment on the impact of the thickness of catalyst layer on the limiting current in particular? And how would you define the limits of catalyst layer thickness in RDE studies?
Well, I think there is a good paper that was written in 2008 by the Stamenkovich group, showing what is the effect of the catalyst layer on the limiting current and on the Levitch plots. So that would be a good start, to look at. I'm not sure if I've never done any testing on non-precious metal catalysts, but you want your limiting current to be close, as close as possible to the value that it should be for, based on the Levitch equation. So. Shaman, you have any other comments on this?
No, I mean, I have seen this problem in presentations with non-precious metal catalysts. I don't do a lot of it, but the limiting currents, are all over the place. And in the case of non-precious metal catalysts too, a separate protocol is necessary, and we haven't reached that point.
Okay, so a listener wants to know what the surfactant was, the one that was used in the non-naphthalene inks.
Yeah, the surfactant was a non-ionic. I tried a whole bunch of surfactants, but finally settled on a non-ionic surfactant called Triton X100. It's very common and used in many labs. And the reason to use it is hopefully it doesn't cause any contamination because it's non-ionic.
Okay. So is there a limited amount of catalyst that can be put on the rotating disc electrode, in the absence of a binder?
No, actually, as you saw in the slide with the effective loading from 0 to 80 micrograms per centimeter square, you can use any amount of catalyst that you want. But as you saw in the plot, as the film gets thicker, obviously you have more oxygen transport issues. So I would stick generally to 18 micrograms per centimeter square or lower for inks with and without Nafion.
Okay. Listener wants to find out what the best method to measure the electrochemical area is.
Well, CO is probably the most accurate method, but it's not necessarily feasible in every lab. So copper electrodeposition is another good one as well to determine the platinum surface area.
I agree.
Fine. And that's an interesting one. Can RDE be used for oxygen evolution reaction characterization?
Yeah, that is a good question. One of the things is for PEM fuel cells, we use glassy carbon discs on which we deposit the catalyst. So really you cannot take it to very high potentials. If you do, it'll start pitting and so on. Now, we also do some of the durability studies for PEMFCs on a gold disc. Hopefully the gold is not going to affect the activity and you can deposit the film on it. So if you use a gold disc as the substrate, you could take it to high potentials. The only time I've done it is to look at corrosion, scanning the voltage all the way up to 1.8 volts. So yes, you can take it to high potentials if you change the material of the disc. I'm not sure how much information you can get about, how good a catalyst is or not for electrolysis using this technique.
Okay. So another listener wants to find out if there are MEA oxygen reduction data by linear scan voltammetry, which we can directly compare to oxygen reduction activity measured by RDE. If so, as he states, is it comparable to the activity measured by the RDE method?
So when we take data in MEAs, we usually take it at 10 or 15 minutes per point. But of course, it is possible to do it at a high scan rate. I don't remember recently taking such data. I have taken it in the past. The thing is, even if you keep the protocol identical for MEAs and RDEs, as I pointed out in the first slide, there are 10 other differences. I mean, for example, the electrode is completely flooded in RDE. It's perchloric acid. You don't really need Nafion. There are so many differences in the electrode structure itself that I don't see any reason why the data should be comparable, although just by chance they might be. You're definitely going to get higher values for activity if you scan it in an MEA as opposed to taking 15-minute data points.
In your opinion, what is the maximum allowable time between preparation of catalyst inks and RDE testing? And what kind of difference should be expected between inks tested right away and inks tested, for instance, the following day?
Janik, you want to take that? Yeah.
My experience tells me that I typically, the day after, I usually get better films, and I get, numbers are better than doing it on the same day as making the fresh ink. And for some catalysts, even letting the ink steer for a couple of days, instead of just one day, it makes the film better, and I get better activity. So it's going to be catalyst dependent, but typically I think you want to sonicate your ink. To prepare the ink the night before, let it steer overnight, and then test it the day after. Typically, for me, that works better. But it could work. You could get good activity on if you have a good film. But for me, my experience tells me that it's better to wait the day after to do the testing after you make the ink.
So in our case at NREL, we make fresh inks every day. We can use it the next day too. It really depends on how good the dispersion is, because if you sonicate it, for example, without Nafion and without surfactant, if it doesn't disperse very well, it's going to flock and settle down. So you would have to sonicate it again the next day, and it may not be so reproducible. So it definitely depends on the type of catalyst, how hydrophobic it is, and how well dispersed the ink is. There's no one clear answer, but I agree with Yannick. You can use it for a day or two at the most.
And actually, there is, just to comment, I think there is a paper as well by Peter Strasser. I don't remember if it was a few years ago that they showed how ink or kept on the on the shelf, how that affects the performance after a few days and things like that. So there are a little bit data in the literature about that.
Okay, on the titles, on the slide titled ECSA Impact of Ink Formulation, you discussed lab-to-lab variability of ECSA focusing on different ink preparation. Should you also include the batch-to-batch variability of the catalyst material?
Well, I think yes, but that would I don't know, it would be like I said, I mean, if you look at, I don't know, I'll take for example the the Nissan data and the NRL data. I mean, it's they are very comparable, and even the poly data. I mean, it looks to me like if you don't pay attention to the ink, the ink optimization, that's going to really affect the way your ECA value is going to be. And actually, it's the one after that, I think, or before that, the slide before before or after that. I think it was before that. Yeah, this one. Yeah. So again, it really depends on the ink optimization. The first paper, like the Nissan paper, it was optimized ink. And I think the poly paper and the NRL paper, the ink composition is about the same, and they get about the same values. And so I think yes, you might have some problem with the reproducibility of the catalyst, but ink formulation is really the big thing for me here.
Okay, I think we have time for just one more question, and the listener sent in a question regarding the quality of the rotating disc electrode film and layer thickness. Do you measure the particle size distribution of the inks you make? And do you use those as a guide to control the thickness of the rotating disc electrode thin film layer?
We do look at the particle size distribution, TEM and so on for some of the inks, but that doesn't guide our use of a certain loading or thickness with film. The two are kind of different.
Well, I think if you keep your platinum loading, between, I would say between 10, to 25 micro, gram platinum per centimeter square, you should be, okay. And again, if you do, like leverage analysis and things like that, you can see how, if your film is too thick, and your limiting currents are not going to be what is predicted by the, by the leverage equation. So, that's a guide that you can, you can keep when you do, you make your films, is by, making sure you get the right limiting current and things like that. So.
All right. Well, I think we're at the end of the webinar, so I just want to take a minute and just thank everyone for joining today, and especially our speakers. And just remind everyone that this webinar was recorded, so we will post to our website in about 10 days the recording along with the presentation slides. And just remind everyone to check back. This is a series, so next month we'll have a new topic. So I encourage you to visit our webpage and sign up for our newsletter to be informed of future webinars. Thanks, everyone.